test. So I finally got myself set up here. So take your time though to finish up the quiz 17, and then we'll go over both of them in just a bit. But try to wrap things up here in the next minute or two. All right, when you're done with quiz 17, please turn it over, pass it towards the middle. I'll come get it. If you're still working on it, try to wrap things up. And then, of course, you can keep quiz 16B to yourselves because we'll go over that together. That was just because I felt like I needed to have another example for you to practice. 17, great. Great. Some 17s here. Good job. All right. Excellent. Thank you. 17. All right. I'll come back. All right, so now if you're not done with quiz 17, you should start panicking, try to wrap things up, and I'll come get the final few of the 17s, and then you can work on quiz 16B. Are these 17s here? All right, both of them? All right, don't want to take the wrong thing. All right, so let's see, any other seven? I guess we've got a couple here. Got a 17. All right, great. There's, got one, thank you. Hard to tell. It's the problem with having two that look identical or similar. I guess we got one here. I think I got them all. Is that right? Are there any other quiz 17s? Before I pull out the stapler. Okay, let's do it. All right, let's go over this quiz 17. Wasn't too bad, hopefully. So here it is right there. And so this is hopefully similar to what you did on your homework in some regards, although I think there was a little bit of, I don't remember, there was some things that might be, it's the same idea as the homework. So what's the claim? What is it that we're claiming here? Well, it says that, let's see, financial analyst believes this upcoming year will have higher proportion of companies. So higher proportion sounds like there's a bigger proportion. So that's what this person believes. However, I'll actually, for the claim, I'll take multiple answers for this because you do have two competing points of view here. You have the initial statement, this, that says that the proportion of companies who pay dividends is 40%. That's P is equal to 40%. And then you have the financial analyst's claim. So there are some competing claims here, but I think the one that I was hoping for was this, that the this something like this, or P is greater than 40%. The proportion is bigger than 40%. So then the opposite of that claim is that the proportion is less than or equal to 40%. And then the null and alternative hypotheses. And here's what I'm looking for is that you're writing down all of the symbols. I'll show you the wrong way to do it in just a minute. I know that's always dangerous because whenever you see the wrong way to do it, sometimes some people gravitate towards evil and they want to do the wrong thing. But here's the wrong way. Don't do this. Let's see, where's the right way? There's the right way. So you see the difference there? Here I have all of the symbols. Here, what is it? What is less than or equal to 0.4? The null hypothesis. What is this? Yeah, so put in this symbol here. So anyway, so then you talk, right-tailed, left-tailed, two-tailed. You're always focused on this alternative hypothesis. And look at that symbol. It looks like an arrow pointing over there. That's right-tailed. Okay, so then we move on to the medical assistant. Let's see, claim. Right there, you've got the word claim. Different, this. So the claim is that the average is different from 220. Hopefully that was pretty straightforward. And then the opposite is that it is equal to 220. Oh, by the way, I should back up just for a sec. Just to be consistent with our homework, I am happy for you to have either that or this as your null hypothesis. So either the thing in purple or the thing in pink, and you could use it as a percentage or a decimal, I don't care. However you do it is fine. So just to allay any fears or concerns. Okay, getting back here, null and alternative hypotheses. The null hypothesis is the one with the equals in it, not the not equals, the equals. So remember, have all of your symbols, and then the alternative is that the average is not equal to 220. This one, not equal to, it points both ways, left and right. So two-tailed. So there it is. That's what I was hoping you'd do, and hopefully everyone did something like that. There's no sentences here. We'll get to the sentences either today or Wednesday. I don't know which. But we'll just we're basically slowly working our way through the basics of hypothesis tests. And you're going to use this same structure for every hypothesis test from here till the end of class. So that's why I want to be careful and go slowly. So is anyone confused about any of this? Like, why is it such and such? Or I'm not sure what, because we got to iron these out now. It's kind of like when we do Excel. It's way better to deal with the issues at the front end rather than in 2 weeks say, I didn't understand that first thing you said 2 weeks ago. It's like, oh, come on. You've got to go back in time now. So no major issues. Okay, so let's back up because I wanted to just take a look at this confidence interval again. And if you haven't finished this, just take a minute. I'm just going to leave it up here for just a sec for the people who are watching the video from home because we do have a few absent people today. Oh, boy. Okay, so you've had plenty of time. So at least you have, and the people from home have too, because they could always pause the video, couldn't they? Okay, so I gave you back quiz 16, and you did really well on that. Some of you had a little trouble identifying like the population proportion P hat, it's got a hat on it. It's this one, come on. You could have just pulled it right out of the chart. But anyway, this one though, on this version, which is more similar to what you'll see on the exam in a couple of weeks, I don't give you that number and you're gonna have to figure it out yourself. But how hard is it to do this? It's not hard at all. We just say, okay, that is the proportion from the sample. It even, point estimate for the population proportion. It's the proportion from the sample. Let's actually do it. 49, sorry, I can't see a thing up close. 49 divided by 120, and I got 0.408 on my calculator. So that's what would go here. Not that, 408. So you could either write that as 408 or 40.8%. Great. Okay, so next is, you'll notice that I left off this. Now, this is not heavy lifting. The Excel is doing all the hard stuff for us, isn't it? Like the standard error, whatever that is, and then the margin of error, those are horrible. And Z star, those are the hard calculations. So I'm having Excel do all the hard stuff for you. You just have to piece it all together. It's not that hard. Margin of error, p hat, hopefully you were able to do this, but let's go ahead and do it nonetheless. I've got 0.408 plus or minus the margin of error. And that's going to give me, so honestly, you write that on a test, I'm like, yeah, great, good job, check mark, smiley face. But what you're probably more likely to do is do what we did on the homework, and that is to write this as a sort of a interval. So let me do this on my calculator. 0.408 minus 0.092. And I got 0.316, and then 0.500, is that what it's going to be? 0.408 plus 0.092. Oh, sure, I should have been more confident in my mathematical skills. Okay, so there it is. So that's what I'm looking for, is an interval, or this is fine as well. Finally, the complete sentence. You'll notice that on the quiz that I gave back to you, quiz 16, the first one I gave you sort of the template. I just wanted to remind you, give you more practice. And then the second one, surprisingly, there were a couple of you that still had trouble with that second one, writing the sentence out, but it's always going to be that same sentence. Let me write down what you should have in your head, hopefully by now, and that is that I am so confident, that the true something is between two numbers. So I'm going to put those two numbers in. Put them in order, please. Don't put the bigger one first. Okay, so there it is. Let's see, how confident am I? It looks like I'm 96% confident. Isn't that what it says? Yes, 96% confidence interval. So that part's easy. Now, as far as the true what? Okay, well, look, most of my problems that I give you on exams and quizzes will have the words in the stem of the problem. Whose? Is that spelled right? Shouldn't it have an E at the end? Yeah, I'm no English major. Okay, I'll put an E at the end. Yeah, just must have been too early or something. Okay, so notice that I can just copy that down. What is it that I'm interested in? I'm interested in the true proportion. And if you're dealing with proportions, don't give me an average. Don't tell me average when we're doing proportions. Proportion of MVNU students whose, does that look better? Yeah, that looks better. Okay, whose favorite pet, so you can correct my English if you want to, is a dog. There, beautiful. It's so beautiful. The true proportion. Notice that that's just comes right from the stem of the problem. And this is also the case with the quiz that I gave back to you. I don't have a copy right in front of me for some reason, but oh, I shoved it in here. Let me see. Yeah. Okay, so the pillows. Notice that the very last sentence in that number 1, if you have quiz 16 in front of you, the pillows, it says 98% confidence interval estimate of the mean number of pillows in MVNU dorm rooms. So there it is. That's the what you should have filled in the blank with. And then the same thing goes for the second one. I won't read it to you, but you can usually get a hint from the stem of the problem as to what to write your sentence. So there it is. All right, so questions, concerns, anything that I got wrong or that you just want to complain about or what have you. By the way, these UCL, LCL that I left off here, those are just those two numbers there. So if I'd given you those numbers, it would have been way too easy. But you can construct your confidence interval. I have confidence in you. You can do it. All right, we're on to new things, new challenges. Let's go on. So hypothesis test basics. Okay, so what we're going to do today is we're going to pound through the rest of the basic instructions for the hypothesis test, and then on Wednesday we're going to put together our confidence interval, or not confidence interval, hypothesis test gold spreadsheet. So you know how we have the confidence interval gold? Well, we have a similar deal with the hypothesis test. You won't want to lose that. You want to be here on Wednesday, and if you aren't, you're going to have to just watch the video and just pause, get that thing typed in properly because you'll need it to do your homework. So today, though, let's finish this up. What is hypothesis testing? We've already done these first 3 steps. We're going to make a claim. What is it that we're testing? We're going to do the opposite of the claim. We're going to state a null and alternative hypothesis, and we're going to make sure that the null hypothesis has the equal sign. So we've got that. Hopefully this is all straightforward for you at this point. Once we have all of those things, what we're going to do, oh yeah, left, right, or two-tailed. That'll be important when it comes to interpreting the results. That's the only reason why I'm making a big deal about this. That's why I've kind of made that as sub-point 3a. Okay, so next, we have to have alpha. Alpha is we kind of talked a little bit about this. What's your threshold? What is your threshold for making a mistake? How important is it to you to make one mistake versus the other kind of mistake? And just to remind you of this, let me just show you this picture again. I know, there he is. So that there's 2 different types of mistakes you can make. One of them might have more deleterious effects than the other. In this case, this is with the parachute jumping out of an airplane. You don't want to make this mistake. What is this mistake? This is the mistake of assuming that the chute will not fail. You're rejecting this when in fact the chute does fail. That does not, you don't want that to happen. So you would adjust your alpha level accordingly. And when you make alpha really low, it avoids that kind of error because alpha is the probability of making that kind of error. It's easy for mathematicians, or for you in particular, to control that. It's easy to control this. This is harder to control, so we just do our best to, adjust as needed for this. So this is the opposite kind of error where you think that the parachute will fail, but it really wouldn't have failed. But what's the harm in that? In this case, what's the harm? Now, if you're dealing with some drug trials and you think that the drug really doesn't work, but it really does work, that might be, depending on what's going on. I don't know. I don't want to, interpret this for the scientists who actually do the work. I'm just pointing out that there are 2 types of mistakes you can make in any hypothesis test, and you can only control one of them, and so that's what we do. Alpha is the probability of a type 1 error. Alpha is the probability of concluding that the null hypothesis is incorrect when really the null hypothesis is correct. So that's what alpha is, and so you have to pick your alpha. Now, not to worry, whenever you're doing problems for me on the test or on the homework, you're going to be told alpha is equal to such and such. So you don't have to make that decision, but you do have to make note of what alpha is. We'll see this in just a bit. Next, we're going to determine which distribution you will use. And this, again, the point here is that you're either going to do a proportion. You're going to use the normal distribution. And if you're doing a mean, then you're going to use the t-distribution. Now, when we get closer to Easter, we're going to throw some additional distributions in there. We've got an F distribution. We've got a chi-squared distribution. You're going to love chi-squared because it involves M&Ms. But yeah, so there's other distributions, but for now, those are the only choices that we're going to deal with. So then next, compute the test statistic. We'll get to this in a bit. So this, oh, here, I should say this stuff, we're going to have Excel do. So we're going to do it on Wednesday. We might get started with it today, depending on time. If I don't goof off with too many magic, I've got my cards again in case we have time. I also have another magic trick up here to show you. And then we're going to make a decision to reject or fail to reject the null hypothesis. And we'll talk about that. And then you'll summarize the results in a complete sentence. I will give you a template that you can fill out, not to worry. Okay, so far so good. So there's that long list. Now let's go on to this. Yeah, now it's time for this. So the thing that I'd like to focus on today is understanding these steps down here, the back end. So like I said, you're gonna let Excel do the hard work of doing all the calculations. So, but once you have those numbers, what do they mean? That's what we're going to deal with today. So to help, let's do some more statistics you can use. And these are this is literally some statistics that you can use on our next exam. So where is this? This comes, wait, I don't think I've shared this with you. I hope not. Yeah, it seems really familiar. Maybe it was last semester when I did this before. Oh, such a fun, this is from 2011, but it's still super applicable. It's the effect of acute increase on urge to void on cognitive function in healthy adults. I think you can probably guess what that all means, but just in case, here's the methods. You have 8, I know, super small sample size, terrible, but still so much fun that I had to share it with you. 8 young healthy adults have consumed 250 milliliters of water every 15 minutes until they could no longer stop going to the bathroom, basically. And performance was on standardized measures of cognitive functions. You wonder, what are these? These are math tests. So basically, you can imagine if someone said every 15 minutes you drink a cup of water. Okay, 250 milliliters. Is that about a cup? That's a fourth of a liter. How many cups are in a quart? 4 cups in a quart? I think so. Yeah, so, oh, look, yeah, thank you, Easton. Okay, it's okay. Okay, thank you. Yeah, yeah, science man. That's all right. So guest lecturer Easton is helping us out. But anyway, yeah, so a cup of water every 15 minutes, and you keep doing that. So every 15 minutes, the scientists are like, here's your cup of water, glug, glug, glug. And then take this standardized math test, and then cup of water, glug, glug, glug. Take this. So every 15 minutes, you have the same thing happen. Now, here's the data. Oh, here, by the way, first of all, here's the results. I love this statement. Sensations of the urge to void and pain increased with time. Okay, so the longer you hold it, it's going to hurt more. Okay, but then this is the important thing for you. Having an extreme urge to void exerted a large negative effect on attenuational and working memory functions. These cognitive functions return normal levels after mixture. This means peeing. So, they drink, and they get worse and worse at their math skills, because that's basically what they're giving them, is like basic math tests. And then after they go to the bathroom, it gets better. The reason why this is an important thing for you to know and statistics you can use is because if you're sitting in my exam and you're like, oh, I gotta go, I'm always puzzled when someone's like, can I go to the bathroom? I know, you were in high school once and I realized that you had to have a hall pass. But for me, I want you to go and take care of business because I know you're gonna do better on my exam if you take care of business. Okay, so that's one reason why I wanna show you this. Oh, here's the graph. Look at this. Here's like, this is how subjective rating, I guess this is how like bad they're doing. So things get worse and worse and worse, and then get better again after they go to the bathroom. So, and how long is this? This is 150 minutes. They're sitting in this room for 2.5 hours drinking. That's 2.5 hours. That's unbelievable. I mean, Yeah, I guess they could only convince 8 people to do this. But okay, so that's one reason, is to show you, I want you over here when you're taking my exam. I don't want you up here somewhere. So take care of your business and then you can come to the exam. Now, the other reason why I wanted to show you this is because of this. Because every time the scientists use statistics in scientific research, you'll see these things. You'll see confidence intervals, but you'll also see things like this, numbers, and those numbers usually have letters associated with them. And finally, this p-value. So the p-value is the thing that, I know it's kind of like a double entendre, but the p-value is what we're really interested in here, is what is the probability. So this p-value is a probability. And oh, I should point out, just back up one, that I just screenshotted the actual paper, that they're using the F distribution here for a couple of reasons, which we'll get to when we get to analysis of variance. But so that's what that is. So they didn't use the T distribution or anything. It's the F distribution. They were comparing multiple states. We'll get to that, like I said, when we get to the analysis of variance. But it's a p-value. That is step 6 on our list. Compute the test statistic and the p-value. They did a great job over here. They computed the test statistic. There's the F. Notice right there, F is 21.3 and the p-value. And they just said, hey, p is really small. Okay, so, what is this? Oh yeah, I wanted to point out that that was the biologists. Now we get the psychologists involved. And the psychologists did something similar, which I think that they're using some interesting language here as well. Inhibitory spillover, increased urination urgency facilitates impulse control. What they found was that if you have kids go into Walmart and ask them to go shopping, they spend more money when they don't have to go to the bathroom. It kind of makes sense. I mean, you've probably been in this situation where you're in the store and you're like, I gotta go. Let's just get the essentials, and then you're out the door. So that's kind of the experiment they went to. So here, if you have to go to the bathroom, you're able to resist more immediate temptations in monetary decision making. So I didn't want you leaving here thinking that if you empty your bladder, everything is going to be well. Sometimes not as good. So let's go on. So determining this p-value. So the p-value, that's what we want to talk about now. And this is the probability of obtaining a sample. So this is complicated stuff here. It's kind of hard to wrap your mind around. But here's the idea, is we're going to assume that the null hypothesis is true. And then we will do some math. Well, Excel will do the math. And we'll compute this probability. What's the probability of obtaining a sample statistic as different or more different than whatever parameter specified in the null hypothesis as what you actually got? So you get this unusual result, and you say, this is unusual. Well, what are the chances that I get that unusual result if we assume that the population is such and such? So like here, in this class, what is the probability that the 2 exam versions were as different? Remember, one of the exams had an average of 89, the other one had an average of 81. That's a pretty big difference. But what's the chances that that just happened by random chance? That by random chance, the one that got the lower score, I just happened to randomly give it to students who normally would have done more poorly on the first one if I'd given him that one. So that's the sort of a probability that we're looking for here. So we're looking for that probability. It's a hard probability to compute. Fortunately, we have Excel to do it for us. So yeah, really hard to wrap our minds around this. That's why I did that magic trick last time. The idea that if I'm just guessing by random chance, then the p-value for each of my little things, like when I'm able to tell you the suit of a card just by knowing the number, so this is an 8, and it turns out that it's a club, that's a 1 in 4 chance. Not very, I mean, here, just to prove that that's not exciting, I'll do this. I won't even look at this one, and I'll just say it's a heart. Oh, it's not. Well, but if it was a heart, it wouldn't be that impressive, would it? Here, let's see. That one is a diamond. Man, maybe I should guess spade. Okay, well, okay, so but it's not surprising. It wouldn't have been surprising. Be like, oh, you got lucky. So the 0.25 would have been the p-value for that experiment. Now the second one where I said, okay, I'm gonna guess the suit, not the suit, the value of the card based on the suit. So I see that someone says, oh, that's a diamond, and I say, oh, it's the 10 of diamonds. Well, there I have a 1 in 13 chance. That's much more interesting, but still, it might not be interesting enough to surpass your p-value, and you might say, well, still, you could have just gotten lucky. But then the third one, where it was a 1 in 50 chance, that was impressive because that's a 2% chance that I would. So my p-value there was a 2%, 0.02. And so the lower the p-value, the more impressive the thing is. So you want a low p-value. That's why these researchers back here were so bragging about their super low p-value. So p-value is the probability. I mean, one way to think of this is the probability that it's just random chance. Okay, we got to do another magic. Okay, I guess we have to talk about this first. Determining the p-value. So this is the too many words. Let's draw a picture. So the technical way of drawing a p-value is this, or to compute a p-value, and this is what's happening on the computer. So I'm just going to have a pretend that this is a right-tailed test. Right-tailed, just to have a just to have an example. So you have the null hypothesis here. And what do I mean by that? I mean, the null hypothesis always has an equal in it, right? So the null hypothesis is that the average is equal to 100 or whatever. So whatever the null hypothesis is, you put that in the middle. So if the null hypothesis is true, then I'm going to grab a sample. The sample is never going to be exactly right there. It could be over here. It could be over here. It could be somewhere. But it might be, say, up here somewhere. So let's say that this is my sample. So with a right-tailed test, and you could do the changeover if you think of a left-tailed test, a right-tailed test, you're going to ask yourself, what are the chances, what's the probability of having my sample be that far? Is this a far distance? Far? Question mark? I don't know. Well, the way we're going to determine is we're going to compute this probability. What is the probability that my sample is either that far or further from the middle? So that is the p-value right there. Kind of looks familiar, doesn't it? It's a normal curve, well, or a t-distribution, and you're computing a probability based on this thing, and you can use Excel. In fact, you'll see when we do this on Excel, you're going to see that we use exactly what you would expect, and that is you're going to use norm.dist of this thing. So you'll have all the numbers in Excel on Wednesday. So that's how the p-value, by the way, if it's a left-tailed test, it'll look the same, only mirror image over there somewhere. Two-tailed test is a little bit more complicated. Here, let me just show you. Let's say that this is a two-tailed test, just for the sake of argument. Let's say it's two-tailed. In that case, what we're going to do, because it's and this is going to feel a little funky, but it's okay. What we're going to do is we're going to take this sample and we're going to say, well, two-tailed means either smaller or bigger, and so if my sample is over here, I really need to sort of account for the fact that this could be on either side. And so what I'll do is I will make a sort of a mirror image over here of the sample, which this isn't the sample, this is just sort of a mirror image of that. And then the p-value is actually both of these. So two-tailed, both left and right. But once again, we'll have Excel do all of this, and that'll help us out. Okay, another magic trick. So just for fun, so what I have here is just a little bit of math for you to do. Not too hard. You might need a little piece of paper though, especially if you're not good at doing it, arithmetic in your head. You're going to choose any two-digit number. For example, you could pick 48 or 97. Don't pick one of those though, because then you would just be, doing what I want you to do. So pick one of those, or any number, any two-digit number will work. And what you're going to do is you're going to add the two digits together and subtract the sum of those two digits from your original number. Just to give you an example, if I chose 48, I would do 4 plus 8, and I'd get 12. And then I subtract 12 from the original number, 48. And do that on your calculator if you need to. If you did 97, you'd do 9 plus 7, and then subtract that from 97. Once you have an answer from part 2, I need you to focus on that answer, think about it, and then I'm going to show you a picture on the next slide, or actually a chart. On that chart, there are 100 symbols. Out of those 100 symbols, you need to very quickly find your symbol. Your symbol will be underneath your number. So the numbers are listed in order from 0 to 100, I think it is. Maybe it's not 100. It looks like 90 numbers, but whatever, close enough. So, so they're going to be listed. You zoom in on your number. See if you can find it quickly, because I'm going to pretty quickly move on to my prediction. So find your number. So you understand? Anyone confused? You got your number? Number from part 2? Okay, so find your number on this slide. Look for the picture. Ready? Did you find your picture? It's this. Thank you very much. No applause. Okay, well, it's okay. Anyway, yeah, so so you might wonder, how does that work? Well, first of all, so you might wonder, what are the hypotheses? I'll go back in case you got it wrong. If you got it wrong, yeah, this is your symbol, by the way, I guarantee it. So here are the hypotheses. Null hypothesis, that's the no difference hypothesis. Usually sometimes it's called the chance hypothesis. I just got lucky. I got lucky and I predicted what your symbol was. Alternative hypothesis is that I can read minds, or probably there's some sort of math involved. There's trickery, and that's more likely the case. So the p-value, by the way, the p-value would be 1 in 90 or so. Yeah? Yeah, your answer. Nope, not the first number. Okay, well, we'll go back and you can see now that we've seen, now that everyone's seen it. Well, we'll go back anyway. So so if you believe me that there were 90 numbers on the screen, then the p-value here, the chances that I would just get it by luck would be 1 in 70, or 1 in 90, sorry about that. And so that's so low that you're like, I don't think that this is correct. I think that there's something fishy going on, and that there's probably some math involved. So let's go back. I'll show you the math if you're curious. So you take 2-digit number and you add the digits and subtract from the original number. I'll actually do this here with 97 minus 16. You get 81. Everyone got a multiple of 9 when they did this. So here, this is 36. If you do it properly, check it out. Your number is a multiple of 9, is it not? It is a multiple of 9. And so when I did this, I cheated a little bit. And when I made this little chart, all the multiples of 9 have bicycles. All the rest of them have other stuff. And I scattered them around a bit so that the bicycles wouldn't all be in one place, but you'll see all the multiples of 9 have bicycles. And so that's why this works, is because I cheated, and all magicians cheat. If I get to this, if I don't get to this trick, we can do this on Wednesday, and I'll cheat some more. You can watch me. I know, I tried. It was hard enough, you know. If I'd done it, notice that I went by 12s or 11. It's 11 across. Yeah, 11. So I was trying to scatter them, but you're right. I wasn't as successful as I should have been. But very nice. So alternative hypothesis is correct. Now, by the way, let's see. What do I want to do here? I'm going to move on. Let's move on. Okay. So let's talk about alpha for just a minute. So alpha is 0.05, and what we want is, so that is kind of our cutoff. So where are you going to be like credulous, and when will you be incredulous, I guess, about this whole situation? So when the probability or the p-value is above alpha, you're going to be like, it could have been just random chance. Because that happens. Random chance, things happen. You know, you get lucky or you get unlucky. So random chance happens, and if you're above alpha, then we're just going to say, it's probably just by chance, null hypothesis. The conclusion is going to be that we're not going to reject the null hypothesis. So here, maybe I should write this down. So here are the options that when the p-value is greater than alpha and the p-value is less than alpha. Oh, those are kind of backwards, aren't they? I was just railing on you guys for putting your numbers in the wrong order. Let me put it in the other order. Give me a sec. So either the p-value will be less than alpha or the p-value will be greater than alpha. Now someone's going to ask the question, so I'll just head you off at the pass here. What if the p-value equals alpha? And the answer is it never is. Never is equal to alpha, so don't even ask that question. So the p-value is either less than or greater than alpha. I'm sure that sometime in the history of the world it was equal to alpha, but it won't be for you. Oh, and if you need to know what to do, if the p-value is equal to alpha, it's up to you. You could just, reject the null hypothesis. Okay, so what happens? That's the cutoff. That alpha is 0.5. If you're less than alpha, this is where you get excited as a researcher. You're like, ooh, it's less than alpha. That means I get to reject the null hypothesis. And notice what rejecting the null hypothesis means. Rejecting the null hypothesis means that it's not just random chance. It's not just that you got lucky and your bacteria just happened to grow a little faster today than they did yesterday. It's that something special is going on. Whatever it is that you introduced into the culture actually worked. So that's what rejecting the null hypothesis means. This is why when you look at the literature, almost all published papers are on over here. Very rarely do people publish papers when you don't reject the null hypothesis, which is a problem for science because you're losing a lot of information when you don't publish about this sort of thing. But this is kind of a failure over here when you don't reject the null hypothesis. Yeah, by the way, I guess that's what this means is you fail. You fail. And right in our language, we say fail. Fail to reject the null hypothesis. I hope you're getting the sense that what we want as researchers, as scientists, what we want is we want to be able to reject the null hypothesis. Because if you reject the null hypothesis, it means that something special has happened. Either I can read minds, or whatever drug that you're testing is actually doing something, or whatever phenomenon your psychologists are studying is relevant to whatever it is that you're doing. So that's when something exciting happens. Here, not so exciting. But when we don't publish about these things, by the way, what happens is that researchers continue to say, well, is this, could this be the case? And then they keep doing it. And the nature of probability is that every now and then, even when the p-value is less than alpha, that's not the correct answer over there. It's a probability. You're never 100% sure. And so this is the probability that the alternative is correct, but it's not 100%. So anyway, I'm almost done with this slide, and then we'll move on to one more thing, and then we'll be done. So reject the null hypothesis, and then the conclusion, and we're going to have this several times. Here's the conclusion is that there is evidence to support, sorry about that, and then you fill in the blank with the alternative hypothesis. So I will put this up. Oh, it's really little, isn't it? There, it's a lot bigger there. I'll put this back up here again on Wednesday, and again every time we have to do a hypothesis test to remind you how this works. But this is just to give you a first, go at this to see it the first time, is that when you reject the null hypothesis, what we're going to do is we're going to say that there is evidence to support whatever the alternative is. So, and remember, as researchers, that's what we're really rooting for. We're like, yes, notice it says evidence. It's like you're in a court of law. Is there evidence to convict? It's not 100% sure. You're not proving anything. Don't let anyone tell you they've proved something with statistics. That never happens. It's always evidence, like a, like a murder inquiry or whatever. And then when you fail to reject the null hypothesis, you're like, oh, I'm down in the dumps. I don't get to reject the null hypothesis, but you still want to sort of, spin this at least sort of, good. And so you say that there isn't enough. There is not enough evidence to support. And then once again, fill in the blank with the alternative hypothesis. Like a politician, you want to put your point of view front and center as much as you can, even when you don't have enough evidence, but you're going to say, well, there's not enough evidence to support this. However, that doesn't say that it's not true, does it? It just says there's not enough evidence at this point in time to support this. Maybe next year we will gather more evidence and we will be able to support this. So it kind of leaves open the possibility that it could be that there's something special going on. Okay, so let's see if we can practice this with this. That's boring. Yeah, why not? We'll do it anyway. So let's just take a look at the first one, letter A as practice. Is this good? Yeah, 45. We got plenty of time here. So ignore the other two, and especially since shared, that's no longer a thing this semester. Last semester it was a thing. People were voting. But let's take a look just at first one. And what I want to do is I want to go through the various steps. What is the claim? What is the opposite of the claim? And then we're going to talk a little bit about what kind of conclusions we might see. So let's get a claim down. And oh, I didn't even do my attendance. Oh, it's a good thing to remind me of here. So give me a sec. I'll do my attendance while you think about your claim. Come on. Statistics, more tools. Okay, so where am I? Random, that's what I wanted. Okay, Trinity, what is the claim? Okay, so there's a number up there. What is that number? 2.3, and what is it that number is supposed to represent? Average, very good. And so this says that college students spend an average, that sounds to me like a statement that's equal, right? That these college students equal, the average that these college students spend is equal to 2.3. Very nice. So there's the claim. Let's get our opposite of our claim. Ethan, what do you have for your opposite of the claim? Okay, so mu is not equal to 2.3. Now we need to sort out the null and alternative hypotheses for this. And we've got Joshua to help us out. Which of those is the null hypothesis, Joshua? Ah, very nice, 2.3. And that means the other one is this one here. So now this is the part that I can't show you yet. We'll do it on Wednesday, but this is the idea that we're going to have our little normal curve here, and we're going to put 2.3 in the middle. There's not enough room down there to put it anywhere else. And then we're going to have a sample. That sample is going to, like average of 2.3. So maybe I'll ask each of you, how many hours do you spend on Facebook each day? None? Okay, well, that's what I figure, is that probably this is kind of dated. But let's say that my sample, X bar in my sample, is something like 0.7. That sounds reasonable. Because there's going to be, you have people like Hayden, but you also have others who are like, yeah, I spend an hour. Wait, can I include Instagram, the whole metaverse, the meta? Maybe. Okay. Well, for hey, yeah, you're unusual though. So yeah, if we include maybe we would include Instagram or whatever, but let's just say that it's 0.7. So what that's going to do for us is it will put a little marker on here, and that is the sample. That is my sample mean. Now, you know how I mentioned the whole p-value thing? Well, you can see here that the p-value is going to be affected by where this thing is, where your sample is. If the sample is further away from the middle, it means probably you're going to reject the null hypothesis. So that's just another way of looking at this, and that is that you could either compute a p-value or you could just compute the test statistic, and the further away this is, the more likely it is that you're going to reject the null hypothesis. So it'll become more clear though when we do this on Excel, because you'll be able to actually see the numbers pop up. All right, so that's it. I guess we'll have to save this one for next time. Let me stop the recording in case you want to come chat. Otherwise, hope you have a great day, and we'll see you on Wednesday.